Welcome everyone to AI Forward, the podcast where we decode the future of artificial intelligence for business and technology leaders. I'm your host, and today we're diving deep into a fascinating challenge, teaching large language models not just to talk, but to reason and act effectively over multiple steps.
Great to be here. This is absolutely critical. We're moving past simple Q&A. Businesses need AI that can tackle complex problems, use tools like search or calculators, and chain actions together. That's where the real value unlocks.
Exactly, and traditional methods like RLHF or RLAAF, they've been useful, but mostly for single-turn conversations or optimizing a final output. They often treat the model's response as one monolithic thing.
That's the crux of it. When you have a multi-step task, like solving a math word problem or answering a complex question requiring multiple searches, an error early on can derail the entire process. It's a compounding problem.
So it's like trying to build a complex Lego model, but you only get feedback after you've put all the pieces together right. If you made a mistake on step 3, you might not know until step 50, and the whole thing collapses.
That's a perfect analogy. And that's precisely the gap this new approach, called stepwise reinforcement learning, or SWiRL, aims to fill. It's designed for these multi-step optimization scenarios.
SWiRL. Okay, let's unpack that. Expert 3, can you give us the high-level picture? How does it work?
Sure, SWiRL is essentially a two-stage process focusing on offline learning. First, you generate a whole bunch of synthetic data where an LLM attempts to solve these multi-step problems, using tools as needed. Think generating chains of thought, calling a search engine, using a calculator step by step.
And the offline part is key for practicality, right? Generating this data involves tool calls, like web searches, which can be slow. Doing it offline means you can generate vast amounts of training data in parallel without bottlenecking the actual model training pipeline. Plus, it gives you a fixed dataset, which helps reproducibility.
Right. Stage 1 is generating these multi-step trajectories. A trajectory might involve the model thinking, deciding to search, getting a result, thinking again, maybe using a calculator, getting another result, and finally producing an answer.
So it's capturing the entire thought process, including the interactions with the outside world via tools. What happens next? This is where the stepwise part comes in, I assume.
Exactly, each full trajectory, say with K actions or steps, is broken down into K subtrajectories. Subtrajectory I contains everything from the beginning up to action I. This is crucial for the next stage.
And stage 2 is the reinforcement learning itself.
Yes, this is where SWiRL gets really interesting. Instead of just rewarding the final answer, like traditional RLHF might do, SWiRL applies RL optimization on each subtrajectory. It uses a generative reward model, in their experiments, a powerful model like Gemini 1.5 Pro, to evaluate the quality of each individual action given the context leading up to it.
So it's like that Lego analogy again, getting feedback not just on the final model, but on whether each connection you made along the way was sound. You're judging the process, step by step.
Precisely. And this leads to one of the most, surprising findings in the paper, actually. They tested different ways to filter the synthetic data generated in Stage 1 before using it for RL in Stage 2.
Filtering, you mean like only keeping the good examples?
Sort of, they tried 4 strategies. No filtering, filtering for trajectories that got the final answer right, outcome filtering. Filtering for trajectories where each step was judged reasonable by the reward model, process filtering, and filtering for both.
Okay, intuitively, I'd bet that training on trajectories that are both step-by-step reasonable and get the final answer right would be the best. Quality in, quality out right.
That's what you'd think, and that is generally true for traditional supervised fine-tuning, SFT. SFT performs best on data filtered for both process and outcome, but for SWiRL, the best results came from using only process-filtered data.
Wait, let me get this straight. You get better results by training the model on reasoning traces, even if they end up with the wrong final answer, as long as each individual step taken was logical given the previous steps.
Correct. Including those process sound but outcome incorrect trajectories actually helped SWiRL perform better than using only the perfect trajectories. It seems SWiRL benefits from seeing examples of logical reasoning paths that just happen to dead end or make a final incorrect leap.
Makes sense from an RL perspective. By focusing only on trajectories with correct final answers, you might inadvertently teach the model to memorize specific paths or answers, hindering generalization. Process filtering teaches a more robust general reasoning skill. It learns how to reason well step by step, which is more transferable than learning specific solutions. As the saying goes, give a man a fish and you feed him for a day. Teach a man to fish and you feed him for a lifetime.
And this focus on the process is reflected in their results beyond just final accuracy. They showed us why RL actually improves the average process reward, the judged quality of each step, even on tasks it wasn't trained on. This provides evidence that it's genuinely improving the underlying reasoning capability.
Building on what Expert 2 said about generalization, this process-focused learning seems key to the impressive transfer results they reported.
Let's talk about those results. Expert 1, from a business perspective, what stands out?
The numbers are strong, double-digit percentage improvements on tough benchmarks like GSM 8K math problems and HotPotQA multi-hop questions. But what really caught my eye was the generalization. Training SWiRL on HotPotQA, which is text-based question answering with search, improved performance on GSM 8K, a math dataset using a calculator, by almost 17%.
Wow, so training it to reason well in one domain with one tool helps it reason better in a completely different domain with a different tool.
Exactly, and vice versa, training on math improved question answering. This is huge. It suggests we might not need to painstakingly train separate models for every single complex task. If we can teach a core multi-step reasoning and tool use capability, it could potentially adapt much more easily. Think about the implications for deploying AI across diverse business functions, faster, cheaper, more adaptable. It's almost like a train once, reason everywhere potential.
That generalization is indeed remarkable. It implies the model isn't just learning task-specific heuristics, but a more fundamental skill of problem decomposition, information gathering via tools, and synthesis. Evaluating this kind of general reasoning capability effectively is a challenge in itself, moving beyond simple accuracy on known benchmarks.
It's fascinating how the stepwise RL mechanism enables this. By rewarding each reasonable step, even within an ultimately incorrect trajectory, the model learns primitives of good reasoning, like formulating a good search query or knowing when not to call a tool and just synthesize, that are applicable across tasks.
I have to admit, when we first saw the process-only filtering results beating the process and outcome filtering for SWiRL, we double-checked everything. It felt counterintuitive.
Expert 4, are you sure you didn't just accidentally break the outcome filter during a late-night training run and then realize it was performing better?
Chuckles, let's just say. Rigorous experimentation led us to the conclusion. But yes, it challenges the common assumption that you only want golden data for RL fine-tuning in this context. Learning from near misses or well-reasoned failures seems valuable here.
It's a fantastic insight, but it can't all be smooth sailing. What are the challenges or limitations here? Expert 5, from an implementation standpoint.
Well, generating the initial synthetic data requires significant compute, especially if you're generating tens of thousands of trajectories like they did. And the quality of the whole process hinges heavily on having a very capable judge model for both the process filtering and the stepwise reward signal during RL. Gemini 1.5 Pro is powerful, but access and cost could be factors for some organizations.
That's true, the quality of the generative reward model is paramount. If your judge can't reliably distinguish a good reasoning step from a bad one, the whole SWiRL process breaks down. Garbage in, garbage out applies to the rewards too.
And model size matters for the generalization aspect. The paper notes that smaller models, like Gemma 2's 2 billion or 9 billion parameter versions, benefited from SWiRL on the tasks they were trained on, but didn't show the same strong cross-task generalization as the larger 27 billion parameter model. So, realizing that train once, reason everywhere vision might require significant scale.
Which brings us back to the business case. The potential ROI from generalization is high, but it requires investment in large models and the compute for both data generation and the SWiRL training process. It's a strategic bet on building more fundamental, adaptable AI capabilities versus narrow, task-specific models.
So looking ahead, what are the biggest implications of SWiRL and this focus on multi-step reasoning? Where does this take us?
I think this is a crucial step towards more truly agentic AI. Models that don't just respond, but can plan, execute sequences of actions, use tools intelligently, learn from stepwise feedback. That opens up much more complex applications. Think sophisticated coding assistants that debug multi-file projects, research assistants that synthesize information from numerous sources, or even AI for scientific discovery that can design and interpret multi-step experiments.
And the offline nature, combined with learning from process-sound imperfect data, makes it potentially more practical and robust than purely online RL approaches that might require constant environment interaction during training. We could see hybrid approaches emerge too.
For businesses, it means starting to think about AI not just as answering questions, but as completing complex workflows. The companies that master building and deploying these multi-step reasoning agents will likely gain a significant competitive advantage in automation and innovation.
From an evaluation standpoint, we need to keep pace. We need better ways to measure the quality of the reasoning process itself, not just the final outcome, especially for these generalist models. Metrics like the average process reward used in the SWiRL paper are a good start.
And the tool use aspect is critical. Making the interaction between the LLM and external tools seamless, reliable, and efficient is a whole engineering challenge in itself. But methods like SWiRL that explicitly train for effective tool use are pushing us in the right direction.
Fantastic discussion. So the key takeaways seem to be: SWiRL offers a powerful new method for training LLMs in complex, multi-step reasoning and tool use. It's stepwise, process-focused RL, surprisingly benefiting from logically sound but imperfect examples, leads to significant performance gains and, crucially, impressive generalization across tasks and datasets, potentially paving the way for more adaptable and capable AI agents. Thank you all, Expert 1, Expert 2, Expert 3, Expert 4, Expert 5, and Expert 6, for sharing your invaluable insights today. This has been incredibly illuminating.
My pleasure, exciting times ahead.
Thanks for having us.
Yeah, great conversation.
Happy to contribute.
Always good to discuss the practical side.
Thank you, important topics.
And thank you to our listeners for tuning into AI Forward. Join us next time as we continue to explore the cutting edge of artificial intelligence. Until then, stay curious. Large language models often struggle with complex multi-step tasks. These tasks require reasoning and using tools like search or calculators. This paper introduces stepwise reinforcement learning, called SWiRL. Reinforcement learning trains models based on rewards for actions. SWiRL is designed specifically for multi-step optimization problems. It uses a two-stage offline process. First, it generates synthetic data showing step-by-step reasoning and tool use. These data sequences are called trajectories. Second, it uses reinforcement learning to train the model on these trajectories. Training happens step by step for each action in a trajectory. A reward model evaluates the quality of each intermediate step. This granular feedback improves the model's planning ability. The study explored filtering the synthetic data before training. Filtering based on step-by-step reasoning quality worked best. This method is called process filtering. SWiRL learned effectively even from examples with incorrect final answers. Filtering only for correct final answers was less beneficial for SWiRL. SWiRL significantly improved performance over standard methods. Improvements were seen on math and multi-step question answering tasks. The technique showed strong generalization across different datasets. Training on one task type improved performance on other unrelated tasks. For example, training on text questions improved math solving ability. This suggests SWiRL enhances general reasoning skills. SWiRL outperformed supervised fine-tuning approaches. Performance also improved with more training data and larger models. Larger models particularly showed better task generalization. The core improvement comes from enhancing intermediate reasoning steps. SWiRL helps language models handle complex, multi-step agentic tasks better.